Okay, so I think it's time to get started. So our next speaker is Châu from University of Chicago. And it's a great pleasure to have you here, although it's online. The title is Generalized Hitchin System. So please, go ahead.
Okay, thanks. Thank you so much for the introduction. I would like to thank the organizers for the invitation to speak at this conference, celebrating 50 years anniversary of Hitchin geometries. And I came to this a bit late in my career, but it's been a very important moment in my career. We're doing automorphic forms, and it just so happened that Hitchin systems brings so much of new light into this and the world of Langlands, as also mentioned geometric Langlands, another aspect of that in the previous lectures by Carlos Simpson. So my talk is about some recent work in collaboration with Benedict Morizet about general Hitchin systems. So many other similar systems. It can also occurs in part in Hitchin geometries, but also occurs very, very much in Langlands program, in the so-called different choice formula and relative choice formula. So let me do some reviews, to many examples of these generalized Hitchin systems. So I just start with with the reviews, and I will introduce this actually very elementary construction of regular quotients, and then there's many interesting problems that can be formulated in this new framework, and in particular, a very simple problem of Cameron coverage, which turned out to be actually quite difficult. So first, let me start with very classical Hitchin's fibration. So we look at moduli space or moduli stacks of Higgs bundles over a curve, and in the Hitchin map. So this is completely integrable system from M to some affine space A. So Higgs bundles is, as you all know, is over X is a pair of E and phi, where E is a G bundle on over X, and phi is a so-called Higgs fins. So it's a section of the adjoint bundle twisted by the canonical bundles. So from my point of view, I really like to reformulate this. It's just a reformulation, but it clarifies things a bit from my side. You just look at the pair of E phi as a map, right? From X to a stack quotient. The quotient here is the Lie algebra G divided by the adjoint action of G and GM, the two commuting actions. So this is not a theorem, this is just a reformulation. It's just literally the same thing as a pair of E phi. When you ask what is this map is the pair of E phi. It's just a reformulation, but the fact that you reformulate it just like it just ease our mind a little bit. In this way, the Hitchin map can be seen as the map from the stack quotient to the invariant quotient. So now I use the // This is kind of usual notation in GIT for the GIT quotient. So G / G is the spectrum of the ring of invariant polynomial of the Lie algebras, right? And so that is a phi space. And another quotient is GM. Now it's the static quotient, right? So now when we have a map from this, by definition, we have a map from the stack quotient to GIT quotient. So the Hitchin map is just by composing, right? The map from X to the stack quotient and composing it down to the GIT quotient. And so A is now a phi space, a map from X to A. So the factor A is the notation for the invariant quotient of G mod G, and so this you want this map A to sit over the canonical bundle. So the canonical bundle is a map from X to B GM, the classifying space of GM, right? So this is the way that I formulate, just reformulate the Hitchin definition of this. So from this, I'm not mentioning on this very deep theory, but no number in host theory is from the point of view classical, from the relation between Higgs band Hitchin vibration and the trace formula is always purely on the lone Bohr side. And the most important thing to understand in very minute details of the geometry of Hitchin vibrations. So in very generally, we can get a lot of information on the geometry of Hitchin vibration by introducing this relative Picard stack, right? This is, in the Hitchin papers, that map from Hitchin map from M to A is generically Abelian varieties, right? Up to some components and up to some isotropic groups. But you can reformulate it very precisely also on the degenerate loci by introducing a relative Picard stack. So it's Picard stack is a stack with a group structure. So this is basically a group in the one of stack, and it varies algebraically over the Hitchin base, and this P act on M relatively to A. So let's say that for every point A on A, you have action of PA on MA, and in this for this classical Hitchin vibration, you have this open dense orbit MA rec of regular Higgs bondons on which PA acts simply transitively. So M contains an open subset, which is basically P, right? So M can be seen somehow as some kind of compactification of P if you wish. Of course, here is to be this is a simple transitive action, so you need a Hitchin section, for example, to identify the regular part of the Hitchin Hitchin modular space with P. So that's what I was just saying, that so one of the basic information you can get out of this calculation is the genetic fibers of PA. The group of component is the same as the component of band G, and which is pi 1 of G, so algebraic fundamental group of G itself, right? So all this is actually on this calculation about pi naught of PA, even for degenerate A, is very important in automorphic theory, the endoscopy theory. That was how I entered into this world, because when I was computing on this pi naught of PA when A varies, I just get endoscopy groups, so which is very mysterious even in the in automorphic forms. So which is really wonderful that from this object is starting from mathematical physics to show up, when you go into some very precise calculation, you got this another object you could deep inside theory automorphic forms. And so to do this calculation, one of the basic tools is called the regular centralizers. And that I am going to introduce this. My talk is about to understand the regular centralizer in very general setting. So let me look at another case, very interesting case with Hitchin vibration for Rion groups. So this had to do with some complex group with some involution. And the first we have the group K, which is the neutron component of the fixed point of theta. And usually it needs to be the group that really matters is something that is almost K, but not quite. So I follow here the papers by Garcia Prada and collaborators, and you want to be K, A to be in between K and normalizer of K. It seems to be the good setting. And so if you decompose the Lie algebra of G and the plus and minus part, so factor K and factor P, so there's easy notation, then A should act respecting these decompositions. And then the Rion Higgs boson X would be H boson E with a Higgs field phi, which is now on P, its value in P, but now it could be twisted by this H band dot. So of course we can by work on many people, and mainly Garcia Prada, Guten, and Riera, we know that this is some more condition about stabilities correspond to representation of pi1 of X value in the Rion group, associated with the evolution. So we can formulate this real Higgs bondons is a map of X into the Stark quotient P mod H, right? And of course, we had to add the GM to accommodate the canonical bondons and any bondon if we wish. And then the Hitchin map in this case is obtained universally by looking at the map from P mod H at the Stark quotient to P mod H, the invariant theoretic quotient. So this is completely the same story I think in the classical case. So we know quite a good deals about this Rion Hitchin map. So if G equals the split in the genetic fibers of H, also union of abelian varieties, but the thing that is now even the connected component is more complicated. It's no longer a group, for example. So as shown by the paper by Hitchin and Shaposnik for UNN, and the genetic fiber is isomorphic to union of 2 to the D abelian varieties, where D actually depends now not just on the group, but on the genus of the curve. So with these number of intersection numbers of the spectrum curve with a zero section or something like this. So that depend on the genus of the curve. And when G is not quasi-split, and the genetic fibers is not a abelian scheme anymore, but it can be some modularized space, modularized stack of bundles. See some example could be with a bundle running through on some spectrum curve and so on. So you really want to set up some kind of general theory that explain on these different examples. And if you set up properly what I call the regular quotient and regular centralizers, and you can all these phenomena can be explained in one single framework. So there's another setting. So again, this setting of symmetric spaces is not just relevant in the Hitchin geometries, but it's also very relevant in automorphic side, when it appears a lot in the relative choice formula. For example, one of in paper by Spencer Leslie and so on. So there's another thing that appears a lot also appears in Hitchin geometries, but really appears in the automorphic side because really the geometric incarnation of one of the most important objects in automorphic theory, which is the choice formula itself. So the Hitchin system corresponds to some kind of simplified version of choice formula called the choice formula for Lie algebras. But for many reasons, we have to understand the real choice formula, and for that corresponds to Hitchin multiplicative Higgs bundles. So what is that? So that over curve X, you only have a G bundle E over X. But now the Higgs field is now on a meromorphic things. So it's going to be automorphisms of E, of the E. So here I write it as G wet G, so G acting by conjugation. So G twisted by G, that is just automorphism of E. But with some, you also impose some prescribed singularity on the boundaries. So if you work it out, work it out a little bit, and you see that the singularities of such meromorphic automorphisms can be classified by some coet. So in the Cartan decompositions of periodic groups, and the condition you impose that this invariance is controlled, so it's bounded by some lambda I. Lambda I is the dominant coet of the group. right? I'm not going to want to go to the group theory details, but that is, this is just a cut on the composition. And once we impose these boundaries and this kind of bound on singularities, we have a good chance to have something that almost finite type vibration and so on. And also this corresponds to the further in trace formula. This lambda would have the Hecke operators. And here is this Higgs boson is just the one to call the trace of the these Hecke operators defined by this lambda I on finite many places on the automorphic spectrum. That's what it is. So this moduli space of multiple Higgs boson with bounded singularities is the geometric incarnation of the trace of Hecke operators on the automorphic spectrum. So there's the whole spectrum side of it, which is very interesting, but I'm not going to enter in that. So somehow it would be very interesting to understand the multiple Higgs bosons, its spectrum psi via some kind of categorical trace formula. And then on the other hand, and to understand what it is on the non-abelian Hodge theory. That is also been my dream for a while, but I don't get any light on that. So, but I think that would be really nice if this can, this can be understood. Anyway, so this is a bit elaborate. You want to now, we no longer have a holomorphic section across the curve, but only meromorphic section with some prescribed singularities. So you want to transform what is kind of meromorphic section into some kind of holomorphic section, then need to enlarge the group, right? Enlarge the group so to accommodate on this section. You want the section is just come inside something is larger than the group itself, and that is called the monoid. There's kind of whole theory of monoid, which resemble a lot of toric varieties, but instead of the torus, you have reductive groups, and that is this monoid theory about, and typical example of Weinberg monoid. So let me I don't want to spend time on this, but basically you have instead of G, you want to look at some kind of extension of G by the maximum torus, something like this, and then M. So that is G plus, and M plus is now normal of phi algebraic varieties containing G plus as open subset with action of G plus on both sides. And so it implies that M plus has its own multiplication. And so now M plus here is really play the role of the Lie algebras in the K-fusion case, right? But so we have the G act on M plus. Here it should be G plus, I think, maybe, I don't remember. By conjugation, and the GM, the scalar action in the K-Lie algebra is replaced by this kind of big torus action, the Z plus action. That's why you need to make this extension to accommodate very large torus. And why do you need this large torus? Because you want to accommodate this lambda I, right? So you can, instead of a map that lies over some Lie bosons, you want this map to lie over some T bosons, right? Some T bosons correspond to these generalized divisors. So I'm just asserting that you can formulate this theory a bit elaborate, but everything just fit very perfectly. Just instead of having one fixed Lie bosons, now you have to work over the space upon some divisors, generalized divisors of the form lambda I xi, where xi are point on the curve and lambda I is dominant coet, right? So over this space of divisors, you have some kind of the whole Hitchin system depending on these divisors. So all this thing is now I think is perfectly set up in this so the kind of long story. I think the first paper on this is how to be a Markman. And then, without knowing these papers, Franken and myself developed it kind of the simplest case. You want to geometrize the trace formula. And then some of my students have been working it out, Boutier, Chi, and Wang. So if you want to look at the most updated, the most complete description of multiplicative Higgs bundles, I would recommend you to look at the theories of Wang, Griffin Wang. Also, I want to mention this kind of multiple setting also be generalized in the symmetric varieties case by Garcia Prada and Guillermo Gallego. So I want another case, I think very interesting case, but you don't understand it very well. That is case of higher dimension varieties. Right? In that case, the Higgs bundles correspond to a G bundle E over this D-dimensional variety X, and the Higgs field is now can be seen as a map, integrable map from the tangent bundle to the adjoint of E. Right? Every vector field you have a endomorphism of E, and the integrable condition correspond to the two vector, the action of two vector field had to commute. Right? So that is how, and then that corresponds to the equivalent to a map from X to the commuting scheme. So CD is now D element inside the Lie algebras, and they're required to commute. So this is a very complicated scheme. This is something that is the most complicated object in invariant theories. And my impression is that, if you understand the commuting scheme, you can even understand everything. That is the kind of the Mars problem in the invariant theory. So on this commuting scheme, you don't know it is reduced, for example, and it's probably not. We have the action of G. So G act by diagonal action on D component, but also have G and D action. The G and D action correspond to what you can recombine the commuting element, right? Some kind of linear combinations. And we want this, then of course we want this map from X to this stack quotient to lie over the classifier of G and D correspond to the cotangent bundle. So a map from X to the commuting scheme divided by G times G and D lying over the cotangent bundle is exactly a Higgs field, right? So you just reformulate it in this way, so that we want to study the invariant theory of the action of G on the commuting scheme. So the Hitchin, now you have also the Hitchin map, also derived of the invariant map, right, from the stack quotient on the invariant of the commuting scheme to the invariant theoretic quotient, right? So with this case again, it's way more complicated than other case, because to start with, in other case, the affine scheme that you start is usually something the vector space or something smooth. Well, not in the multiplicative case. In this case, you don't even know whether it is reduced, so it's very complicated. Not irreducible, not reduced. But we sometimes you can say something about this. All right, so now what I want to do with Benedict is to try to formulate some kind of general framework to understand the geometries of all this object in one single framework. So for that, we want to understand what we call the regular quotient. So we don't really claim any kind of news here. I think when I look back to the book of Mumford and on geometric invariant theory, actually Mumford only mentioned something looked like a regular quotient, but just he doesn't really pay attention to that. Like, I think nobody really studied later that, but it's something very natural when you study geometry of group action. So now let me come to this invariant theory. So now my framework is just a reductive group G acting on some affine scheme M, a finite type of fin K. Right? It's very, very general. So now in GIP theory, what we look at is the invariant theoretic quotient, the M//G, which is by definition is the spectrum of the ring of invariant function, G invariant function on M, right? And by GIT, we know that the close point of M//G correspond bijectively to close orbit of G on M. It's quite remarkable result. The proof is actually quite complicated. In characteristic P require quite a lot of work, but it works on completely generally. So, but now when you look at the original K of Higgs bundles, so what you really need is not the closed orbit, right? What you really want to understand is actually the regular orbit that has the maximum dimensions, right? So the quotient here is not, when you do invariant theory, that is, it's natural. And you look at this invariant theory quotient, and it end up to be classified closed orbit. But the Euclidean closed orbit is something very strange. It's just constructible set. It's not open, not closed. It's not very nice, right? What is intuitively much nicer is actually the regular orbit. The regular orbit is just orbit of maximum dimension, and just by the semi-continuity dimension, M-rad is going to be an open subset, right? So most of the time, even when M is not smooth, M-rad happen to be, in many situations actually smooth things. The regular orbits are very nice, and the idea is actually very simple. We just want to construct a space, not a stack. It's a real physical space whose point correspond to regular orbit. That is what we want to do. So instead of a space of the invariant theoretic quotient corresponds to closed orbit, you want another space correspond to regular orbit, maximum dimension. That is a very simple-minded ideas. So that is what I was saying. If M-rad is smooth, then this I denote by this M-rad G with this kind of fast slash is the space that I want to construct, and because M-rad is smooth, this quotient is going to be smooth, and this end up it's not exactly a space. It in the most case going to the limit for stack, which is close to be a space, and because of this is a construction is rather formal, some kind of descent construction, and you very soon realize that you need some extra datum, which is I prime. So I prime is you need a flat subgroup scheme of the stabilizer group scheme, right? So I rec here is the when G act on M, then you have the stabilizer group scheme, right? And when you restrict to M-rad, then the stabilizer group scheme has a constant dimension. But for the constant dimension doesn't guarantee to be flat, right? There's a many examples. The most obvious and some other typical example when they look at PGN2 acting on itself by conjugation, and then you actually have some kind of regular semi-simon element whose centralizer is not even commutative, right? Does that mean that the centralizers, the residue regular locus is not flat because it on the open subset is commutative, and there's some kind of funny thing that happened on one element, so that means it's just not flat. So we just want to remove that. To remove those funny things. There's something inside, be closed or something like that, which is flat. So the definition of M-rad fast slash G depend on this I prime, and it is the demand for stack. In the good case, when I prime happen to be the whole centralizer, then this is algebraic space. So this is a technical issue. You really need it to make sense of this quotient, right? But in model case, you want to ignore it. Any questions so far? All right, so so just by construction, because we start with M-rad mod G, which is algebraic stack, and this M-rad fast slash G is defined by descent. Then this map actually a germ. It's just really by construction because you mod out by something on the inertia, and this is a germ. And as a job is bounded by something that look like a group scheme, right? A flat group scheme, and it is by general theory actually not a group scheme, but a link. A link is kind of ugly object which is locally a group scheme, but the gluing data is only defined up to inner automorphisms, right? But what happened is this is the group up to inner automorphisms. So it's just a very important point that you can define bundles, principal bundle of a link. You don't need it to be a group scheme, right? And this is only need for this description, like. So in the case that we studied so far, this thing actually is a group scheme because it starts to be commutative. When it's commutative, then the up to inner automorphism doesn't matter. It's just up to nothing. So it's really a group scheme. And most of the case, the regular centralizers happen to be a smooth commutative group scheme over the regular quotient. So another way that you construct this regular quotient as a natural space over which live the regular centralizer. So again, either for the symmetric space for non-quadratic split groups, then this J is not commutative. It's just a I don't know if it's a ring in English in French called the lien, right? I don't remember what is the English word for these things, but it is a group scheme up to automorphisms. So in particular, even it's not a group, bun J actually makes sense because you see the bun J only depend on J up to automorphisms. So even when it's a link, you can explain what I think in Hitchin and his student call non-nabelization phenomenon. That is okay when J is a non-commutative link. All right, so let's look at the example to it's better understand much better. You look at the examples. So for the adjoint action, actually the thing is kind of perfect. You don't because they have this map from G rec /G to G / G from the regular quotient to the invariant quotient. This is an isomorphism. This is why the thing works so nicely on the original Hitchin, the original Hitchin moduli space. Is this works very nicely because over the fibers of every closed orbit, you actually have one regular orbit and only one. So that is why this map from the regular quotient to the classifying regular orbit to the invariant quotient classified closed orbit. This is a bijection and geometric isomorphism of algebraic varieties. And the regular centralizer here, instead of living over the invariant over the regular quotient, it lives on the GIT quotient, and that is the regular centralizer on this A equal to G mod G. So now, it's more complicated case is the conjugation quotient. You just look at G acting on itself by conjugation. And if G is simply connected, or if the derived group is simply connected, then it works the same. In this case, you also have the map from the regular quotient to the invariant quotient is isomorphisms, right? And then the regular centralizer is defined over the invariant quotient. So when the derived group is not simply connected, or just for G is some kind of adjoint group, then you run into a problem, right? Because we know that the invariant quotient G mod G is not smooth, right? You have this kind of fusion singularities on this T mod W, and W is not reflection groups. So, and another side, by definition, the regular quotient is smooth. So what is going wrong here It just because in this case the I restrict to Z red is not flat, right? So to construct the regular quotient, you need to introduce some smaller group scheme which is flat. So in this case, we have to take I prime to be the group scheme of neutron component, and then this construction, the regular quotient is smooth, but it is the limit for stat, and the core space is the invariant quotient. All right, so it's kind of nice that it just the abstract construction, but it explain this kind of bizarre phenomena somehow in the in group theory. When basically on PGN2, when you look at the matrix 1 minus 1, and then the its centralizers is not commutative. All right, and as I said that to understand the multiplicative Higgs boson, we need to introduce this Weinberg monoid, right? So as soon as they are simply connected, and they have this Weinberg monoid, and you have the action of G on M by conjugation, right? And now inside G, there's no difference between the regular quotient and the invariant quotient. There's kind of significant difference on the boundaries, right? There is some very important paper by her and Lustig. So on the in the monoid, in this Weinberg monoid, it makes sense to talk about nilpotent element, right? And her and Lustig classify on the regular nilpotent orbit in the Weinberg monoid, and there's just a large number of them. There are 2 to the n numbers of regular nilpotent orbit, where n is the number of Coxeter elements. So it's really large numbers, and it so happened that is in this case the regular quotient can be covered by many copies of invariant quotient glued together, right? They are going to be the same point on the inside the group, but outside the group it should become different point, and you need to be as many as 2 to the n copies. And this has been kind of this been explained in Boutier theorems in the thesis, when he tried to extend the Sternberg section, right? We have to look at a classical paper by Sternberg where he defined the sections, just this invariant map from G to G mod G in the simply connected case. And to define it, he actually need to an orders between the simple roots to define that is just a Coxeter element, just an order into simple roots. And it happened that at the end two Sternberg sections are conjugate, so that this order between simple root is immaterial. It's not important inside the group. But the same construction of Sternberg can be applied for monoid. It makes given sections, right? But when the different choice of order simple roots give rise to different sections, no longer conjugated. Actually, it ends up to different regular nilpotent element. So that is Boutier prove that when you fix the order among the simple roots, then you have on the sections, and it just so happened that that give you somehow a presentation of your algebraic space as a union of many copies of the invariant quotient, right? And but of course this is still very rough. We don't know how they glue together. They can write it a union. So I think it would be very interesting to understand how these different copies glue together. And combinatorics can be very complicated, but just have it because you have a lot of copies. But this kind of gluing is actually being further well understood in the case of symmetric spaces. So this is work on this have been done by Garcia Prada and Pio Nieto, and also in paper by Hamester and Morrissey. And in Hamester, I think in Garcia Prada and Pio Nieto, they look even very close, but they didn't have this language of regular quotient yet. But in the paper Hamester and Morrissey, they just work on within this framework, and they describe completely this invariant quotient. So so in the kind of almost simple case, so that the only one Deacon diagrams, then this P-reg mod H, this invariant quotient is basically two copies of the invariant theoretic quotient, and it's one complicated have four copies, and they show you exactly how they include together. And I should mention that this phenomenon discovered by Hitchin and Shaposnik can be perfectly explained by this, because when the 2 to the n component, when the spectrum curve meets with the zero section, and then the regular quotient you can undergo kind of two different choice, right? Because you have this kind of the two different choice, and so because of then when you have n different intersection point, then you have 2 to the n section point. So that 2 to the n in Hitchin Shaposnik really had to do with these two copies. And the fact that P-reg fast slash h is two copies glued into some way of the invariant theoretic quotient. So in all this case, up to this annoying problem with the Mundell-Mumford, the regular quotient is actually a scheme, right? It's algebraic space, but it can cover in Zariski topology by schemes, by the invariant quotient. But it actually is not so. This very interesting example. This example, I don't think it come up in Hitchin geometries, but it quite prominent in automorphic theory. Because Generalized quotient, and with easy way we just try to compute this example, and it look really nice. So this is actually GLN minus 1 actually on GLN. So we embed GLN minus 1 into GLN by block matrix, and then by block matrix, and it's just absent, so in this case, you can compute that the MREC fast slash G in algebraic space, in not a scheme. So you cannot cover it by scheme within Zariski topology. Now this is, you can describe it. You have a very nice description. I don't have time to explain, but I'm happy to send you the note. It's very nice description, but it's not algebraic space. It is an algebraic space, it's not a scheme. From the M rep mod G to M mod G, there's no Zariski section, as opposed to the other case considers. Yeah, but the most challenging case had to do with commuting scheme. That had to do with Hitchin fibration for higher dimension varieties. So, for example, this kind of two commuting scheme for surfaces. So, we had two elements in the real algebra that commute. So, it had a kind of functorial description to have a lot of importance, possibly, with action of G diagonally and action of Gn2 by linearly combining the x1 and x2. So in the case of Ng con Gn then you can compute, and you can see that M mod G, the invariant theoretic quotient, is actually the Châu scheme, classifying 0 cycles of length n in A2. Right? If I just want x1, and that is the Châu scheme of A1, and that is just the eigenvalues. So this Châu scheme is some kind of joint eigenvalues of x1 and x2 that define you a point the Châu scheme of A2. That is the 0 cycles of length n is the joint eigenvalues of x1 of commuting operator x1 and x2. So, but you can look at this construction. So you have x1, x2, MREP. So it is in MREP if the common centralizers is the same as dimension of G, which is n, right? And by some classical reason by pre-Chaucer, you can put the MREP actually smooth. And you can try to compute what is, you really want to understand what is actually regular quotient in this case. If you're not understand it yet, but at least there's some very nice, smaller than regular that connect on M cyclic. So M cyclic is the case x1, x2, so that there's operators, the vector space become a cyclic module, so it has some kind of cyclic vectors. Then then it's easy to see that M cyclic fast large actually exactly Hilbert scheme, a zero-dimensional length and A2. So the map from, you restrict the map from a flat quotient to M cyclic, then you get the very classical construction of Hilbert scheme to Châu schemes. That is the famous Hilbert to Châu resolution of singularities. And so I can show you, it can show something larger than Hilbert scheme, right? And so on this is many cases. So what can we say about general things about this kind of regular quotient? And this is very much in the spirit of this Hilbert to Châu resolution. Is almost a resolution of singularities. It's just the fact that our quotient is a bit too big. It's not a scheme. So conjecturally somehow, if you remove something, then you get some a bona fide resolution of singularity. So what you can prove with Benedict is this: if I assume the characteristic K is 0, then the map from the regular quotient to map from M or G is universally closed. So universally closed, that just means that if to put something improper, have the existent part and the uniqueness part of the evaluated criterion properness. And here you can put it, the existent part is satisfied, not the uniqueness part, right? Because it's not separated. So ideally, I think, I don't want to conjecture it, but probably there should be some GIT condition that you cut out the MREP mod G, something that look like Hilbert scheme, which is going to be a resolution singularities of the invariant quotient. Right, so I almost, I don't think that, I don't want to run over time, and I want to discuss the how we can, what you really want, how you can have a hand to compute anything with this kind of very generalized Hitchin system, depending on the G on some any affine varieties. Of course, you cannot do much in general, but you try to set what, how you can compute it. So for that, you have to come back to the adjoint case. You have this survey wrestling theorem. So we have G mod G is the same as T mod W. And that is kind of very nice that when characteristic K equal to 0, and maybe more general than that, you have under one single assumption that there exists at least one closed and regular orbit, right? Then you can, under this very single condition, that lunar Richardson condition, there is one closed and regular orbit, then you can generalize the CRT, Chevalier-Wessing theorems. So, you look at this closed regular orbit, then the stabilized point of this orbit is going to be some reductive group, subgroup of G, H of G, and maybe with a connected component. And this conjugacy class is completely determined. It's going to the same for open subset of M. So this is what we get from this condition of existence of one closed regular orbit. And then it just, with this H, it just F the fixed point of H, right, in M, and NH, the normalizer of H. And then you have this M mod G the same as F mod NH. And this is the generalized Chevalier-Wessing theorem due to lunar Richardson, right? Of course, you need some lunar slide theorem here and need some characteristic 0. But if you in the case, I think if H is a torus, then you don't need anything. You can overcome on AVCAL testing. So in the case of adjoint quotient, there's very one piece of the theory which is actually useful is the Donner-Gesbury theory. There's some can interpret as some kind of Abelian Galois description of regular centralizers. So by you know that the map from T to T mod W's is a finite and flat, and this follows from the Scheffer-Toth theorem. And this what for Donner you call this universal Cameron cover. And this cover in very nice. It's a bit technical, but it's actually precise. This regular centralizer. Instead of just have to leave it to some regular element and take the centralizers, it just form this finite flat map. So this is J is regular centralizers, and this some kind of sandwich between the J0 and J1, which is where J1 defined by just doing the very restriction of the constant torus, and then take the W invariant, and the J0 is the group scheme of neutron component J1. So J0, J and J1 are almost the same. It's just some kind of very tiny discrepancies depending on the root system. So this is actually very nice. This is coming from just a reformulation of Donner-Gesbury theory. But this is actually very important, when there is for example, when you flip and you go from G to G dual, and just happen that J1 becomes J0, and J1 is dual to J dual not, and J0 to dual J1. So this sequence actually flip, and that's how you can actually very clean proof of the mirror symmetries. So for example, mirror symmetry itself depends a lot of this description of this regular centralizers, and also you have two things that depend very crucially on this story of description. This one is mirror symmetries, and the other is endoscopy theory. So that I really want to get a hand on this Cameron cover in more general settings, because it gives you kind of very precise description of the regular part of Hitchin fibrations. So I can give I can give you a rough conjecture. I think that by the end it needs to be more conditioned, but I just try to formulate something that's roughly correct. Not going to be eventually correct, but what you can look for in very general situation. So you know that there exists a closed regular orbit. I know that M a regular semi-simple to be the union upon the closed and regular orbit, right? So this is going to be an open subset of M, and it's very much like the regular semi-simple part of the Lie algebras. And the FRS is going to be the intersection of MRS with the fixed point of H, right? And again, you have this on mod G on the regular quotient. You have this Chevalier restricted theorem for this regular semi-simple part, and here you have the obvious Galois covers, right? You just replace look at FRS mod by ZH instead of NH, where ZH is the centralizer, H is instead of the normalizers, and the Y group is NH mod ZH. And the very optimistic conjecture is that these covers defining on the open subset of M rep fast G could be extended into some flat covers on the regular quotient, and that would give rise to a Galois discriminant of the regular centralizer similar to Donner-Gesbury in very generals. So it so happened that in every single case that I know that this thing works more or less in some, but it doesn't seem to be. It seems to be a bit hopeless to prove in generals. So at least in symmetric case, this is in it already is some. I almost finished. Some slight modification need to be needed because the Y group is not this. You have to replace this lunar Richardson Y group with some other Y group. The choice of the Y group actually important. So in this in symmetric space, the version that works is due to Leslie and James and Morrissey. It works, but you need to modify this conjecture a little bit. So, but I want to end up with some kind of really fascinating case for me, where it works, which is Hyman theorem. So in Hyman theorem, you have this again. You have this M rep mod faster G contain the open subset Hilbert scheme, right? And Hyman, there's this theory of big paper of Hyman's, and the most important technical reason in that is that this Hilbert scheme admit the so-called isospectral Hilbert scheme, Hilbert tin n, which is the finite flat cover of Hilbert n of degree n factorial, right? On the open subset where n points are separate, and you have a clearly n factorial covers by ordering those points. But when you go to the boundary, it's actually very hard to factorially to define how to extend this finite flat cover in flat, and that's what Hyman proved. And there have been very many attempts to produce a more conceptual proof of Hyman theorem. Hyman theorem proof is long, elementary, but rely on this very complicated combinatorics. And I don't know, I'm not sure that there is any kind of more conceptual proof of Hyman theorem. And here I really clearly want to some kind of generalization of Hyman theorem as existence of Cameron cover of the regular quotient. And well, I mean, I'm not completely sure that it's work on every single case, but at least I hope that there's some kind of condition on M and on doctrine of G, so that this Hyman covers or this Cameron cover exists. I think that is all I have to say, and thank you for your attention.
Okay, so thank you very much for your talk. So, is there some questions to Bob? Yeah.
Thank you, Châu, for your very nice talk. Can you comment maybe on the possible use of the generalized Hitchin vibrations in the context of the relative Lagrange program that recently has been exposed by IMSA and Secretariat and Venkatesh?
Yeah, so this is a so-called in this program of Secretariat Venkatesh and Bensfi, there's had to do with spherical varieties. So something had to do with G mod H, right? Where H is the spherical groups, and the trace formula would be G mod H, like G mod H times G mod H, and G acting on this G mod H times G mod H, right? And so in this case, a Higgs field, so to speak, is would be a G bundles and a map, and a Higgs field in value in X square, right, divided by G and twisted by the E bundles. And of course, you have to develop this invariant theory in that settings. I'm pretty sure that all my conjecture will be true in that settings. And also, if you can describe on this regular centralizers, and then maybe a better hope to understand the duality conjecture. It seems a bit mysterious for me, but yes. But I'm completely sure is this construction would be fundamental to understand the relative trace formulas in the relative trace formulas, the one that was Bensby, Secretariat, and Venkatesh needed in their work.
Thanks.
Questions? no conditions for when your special quotient is actually giving you the resolution singularities. You mentioned a specific example, but is there a general kind of setting where it will always do this?
And I cannot hear very clearly the question.
I was seeing that in some cases you were actually seeing that your sort of defined quotient was giving a resolution of singularities in the GIT quotient. Then is this a general phenomenon, or do you know when the other conditions?
Yes. It should be a very general situation that, you know, in the I just come back to this slide. So in very generally, right, assume that, you know, when this M reg is smooth, then this regular quotient is something smooth, right? And usually the M mod G is singular. So here we have some kind of resolution, right? Something smooth that maps surjectively on M mod G. It's just too big. So this M reg faster G is too big. And you need to cut, cut something out of it to make something proper. In the case of the previous case, in this case, you have this M reg mod G is smooth but not separated. But this cyclic condition provides some open subset of it, which is proper as, you know, separated, right? This story between M reg and M sig, I think should be generalized in many situations, and to define a resolution singularities of the invariant quotient.
Okay, thank you. So more questions? No. Let's thank Dr. again, and so thank you very much.
Thank you.